So we're going to start off today. We're only going to talk about titration curves today. And the reason for that is there's a good bit of complexity in titration curves. Just in the fact that there is a lot of information that you can pull out of them and that you can use from them. But one of the really remarkable things about titration curves in general, and this is kind of interesting, is that when it comes to doing the calculations involved in a titration curve, we're actually not putting in any new calculations. Every calculation associated with the titration curve is a calculation you've done already. What it comes down to is recognizing where we are in the curve and knowing what calculation to do at what time. So we ended yesterday looking at this image and the fact that even though both of those substances had the same equivalence point in terms of the amount of base used, the curves could not look any more different from each other than they are. And so we're going to get into the reasons for why that is the case. And so when it comes to titration curves, we can generally think of titration curves in one of three categories. We can see the strong acid, strong base curve, where we are titrating a strong base into a strong acid. We can see the flip of that, where we titrate a strong acid into a strong base. A little bit less common, just because of the indicators we usually use for that. Or we can see interactions of weak and strong. Now, when we talk about titration curves, there are going to be four key areas that we always look at. We want to look at the initial pH. So for a strong acid curve, we're going to see that the starting pH is very low. So this would be the pH of the solution before we add anything to it. And again, we saw in the lab yesterday, looking at the difference between a strong acid and a weak acid. The strong acid at the same concentration had a lower pH than the weak acid at that same concentration. We saw that kind of consistently throughout yesterday's lab. The second region, as the titration is beginning, before we get to that equivalence point, we want to look at that area between the beginning of the titration and the equivalence point of the titration. In a strong acid, strong base curve, what we'll see is that the pH is going to very, very slowly increase. In fact, it's going to look in a lot of ways like it's not changing very much at all. The third point that we will look at is the equivalence point. At the equivalence point, what we are talking about is where do we see that true neutralization take place, where every mole of acid has been matched by a mole of base. We want to make sure that those are equal at each other. And so for a strong titration, because we know that the conjugates are going to be neutral, we would expect the pH to be neutral as well. It should be right at 7. Now, also, as we saw yesterday, a lot of what we see around neutrality depends upon your water chemistry. So if we were to do such a titration in the lab, chances are actually pretty good it wouldn't be right at pH 7. It'd be based on what our water chemistry was kind of doing at that time. Even though we use deionized water, it's hard to get it fully degassed. It's hard to get it fully neutralized and not absorbing any of the carbon dioxide in the air. And then the last point of interest for us is after the equivalence point. At that stage, strong base dynamics take over because we are just adding more hydroxide to the system. And so what we'll see is that the pH is going to rise and then eventually it'll level off. And so this is an example of a strong curve. And we can see, looking at all four of those zones, starting pH is low. The pH change as we get to the equivalence point is relatively minimal. In and around the equivalence point, we see this very sharp change in pH. The equivalence point is at or near pH 7. And then as we go to the top, we'll see it slowly rises and then kind of levels off. So those are the characteristics of a strong acid, strong base pH curve. And on Monday, our Monday afternoon lab is going to explore these kinds of phenomenon more fully. So you'll actually get a chance to do a titration with a strong acid and a strong base and create a curve much like this. Now, another type of titration is the weak-strong titration. Again, this is a pretty common one. This is the kind of one that we would see when we titrate, say, acetic acid with sodium hydroxide. There are a couple of key things that we want to look for. So first of all, we should notice that our initial pH is going to be higher generally than if we had a strong acid. But what's of real importance to us is the fact that at the equivalence point, we're still looking at equal molar amounts of base added to acid present. But because that acid is weak, we know that its conjugate base is not neutral. Its conjugate base, in fact, is going to act as a base. It's going to act as a weak base. And so what that's going to do is it's going to just raise the pH at that equivalence point. And depending upon the nature of that conjugate, it could raise it relatively significantly. One other important thing. That region between the initial pH and the equivalence point, it's got something going on with it. If we think about our definitions, if I have a weak acid reacting with a strong base, I would get water and conjugate base. Well, if we're not at the equivalence point yet, I would have conjugate base and weak acid present in the same solution at the same time. We've got a term for that. It's a buffer. So in that area between the initial pH and the equivalence point in a weak acid titration, we're making a buffer. Because so long as we're not at the equivalence point yet, we're going to have some amount of HA. And so long as we've added some hydroxide, we've converted some of that HA into A minus. And once again, the presence of both of them there, that's a buffer. And if we're looking at trying to kind of predict pH values, we can do that using buffer kinds of calculations, Henderson-Hasselbalch equation, mini ice tables, the whole smash. One other important implication from this, though. Since we are creating a buffer, at the halfway point, so halfway between equivalence point and 0 point, that's going to be our half equivalence point. That point is significant because we will have converted exactly half of the weak acid into conjugate base, which means if one half has converted, the other half has not. In our Henderson-Hasselbalch equation, I would have equal amounts in the numerator and denominator of that fraction, which would mean that the pH I measure at that point would be equal to the pKa of that acid. And so that is really important for us because we can use that information to identify unknown acids. If we have an unknown weak acid, we can do a titration with it. Using a titration curve, measure the equivalence point, work backward to figure out the half equivalence point. And at that pH, that would be the pKa of the acid. That would do a lot to narrow our focus. And then we can do other analytical kinds of techniques to try to narrow down the field. Does this acid react with this kind of thing? Does it give you this kind of product? So this is an example of a weak acid strong base curve. Again, the points of emphasis, the things that you want to notice. We have a higher starting pH. Unlike the strong acid curve, which was largely flat right until we got to the equivalence point, we've got a buffer zone in here. And as you know, buffers will increase in concentration incrementally. So it's not going to be 2, 2, 2, 2, 2.01 as you're going through the pH, as you're going through the titration. It's going to be 2.12, 2.15, 2.19, 2.24. And it's going to just gradually increase as you go because each drop of base is going to affect that ratio. Another thing that we'll notice, we've got a smaller equivalence point zone here. It's narrower because we're seeing greater changes in the pH leading up to it. And this pH is going to be greater than 7. It is going to be basic because of the reactivity of that substance to water. That conjugate base is going to act with water. It is going to produce hydroxide. So just to summarize the differences between those two main curves. Weak acid, higher starting pH than the strong. The pH change in that rapid rise zone, in that zone right around the equivalence point. It's large for a strong acid, it's smaller for a weak acid. The pH at the equivalence point is going to be greater than 7 for the weak acid titration. And this is just a general statement here at the end. The weaker the weak acid is, the more prominent these changes are going to appear. If you've got a weaker weak acid, it's going to start at a higher pH. Its pH at the equivalence point will also be higher because its conjugate will be more basic. Now, what we will see for base acid curves is practically the same thing, just in reverse. So if you look at the curve here, you can see here's our strong base curve. Here's our weak base curve. From a shape standpoint, they look pretty much the same. Just, again, take that image of the strong acid curve and make it a mirror image for the for the strong base curve. Take that weak acid curve and make a mirror image of it, and that's your weak base curve. All of the things that we talked about with strong acid versus weak acid are going to be there also in strong base versus weak base. Differences in the rapid rise region here, differences in the equivalent point, still have a buffer zone here. The buffer zone will give you the pKa, which you can then turn into the pKb since it is a base. If we have multiple equivalence points, like say we have a polyprotic acid, like phosphoric acid or sulfurous acid, or we have a base that is capable of giving up multiple hydrogen, or taking on multiple hydrogens, taking on multiple hydroxides. So the example they're giving here is carbonate ion finding its way down to carbonic acid. What you'll notice in those is that the effects are going to be kind of the same. So this was a weak base at the start. So notice that the pH is kind of on the low side for a base. It's right around 10 instead of like 12 or 13. We've got a buffering region, kind of a slanted equivalence point region, so really not sharp at all. And we've got a second equivalence point there after another buffer region. It just generally looks like you took that curve and you just kind of stretched it out and pulled it further. Everything just kind of looks stretched out, like when you take an image and move it way wider than it's supposed to be. Looks a little distorted. Now, one thing to note about these, really common misconception is that you can use these graphs to figure out multiple Kas or Kbs. Now, the first one we kind of talked about, halfway between initial and equivalence, that would be your first half equivalence point. The misconception is this: a lot of people will try to do the same thing with the second equivalence point as well. Just go halfway between the value and the starting value, like there. And that's not accurate. For subsequent equivalence points, we want to measure them relative to the previous equivalence point. So if this one is here around, let's say 9, and this one here is around 28, 28 minus 9, or I'm sorry, 28 plus 9 is 37, but divided by 2, about 18 and a half. We'd be right about here. So what we're really looking for there is the midpoint between the two equivalence points, not the midpoint between the second and 0. Again, we can see kind of the same thing. This is phosphorus acid. In phosphorus acid, we look at, here's our first equivalence point here at 50. So we would measure the first pKa here at 25. Our second pKa would be the midpoint between 50 and 100, which would be 75. So that's where we would measure pKa 2. And so for weak acids, that is probably the most valuable piece of information that we can get off of a titration curve. And that is using the titration curve to get the Ka of the acid. Because we can use this to get the equivalence point. We can use that to find the concentration. But like I said yesterday, that's kind of we could do that already using indicators. So before we get into this calculations with titrations, I'm actually going to skip ahead just a little bit and come back to the concept, the idea that we were looking at the beginning of this week with indicators. So indicators are usually organic acids of some kind, some sort of organic dye that will change colors as it ionizes, either as H plus is added to it or as H plus is removed from it. And we use them in general to determine the pH of a solution very qualitatively. So take, for example, phenol red. Phenol red is a weak acid. Its pKa is 7.6. When it is unionized, that is, it has all of its hydrogens on it, it looks yellow. When it is completely deprotonated, all the hydrogens are off of it, it looks purple. In between the two, you will see transitions from yellow to orange, orange to red, and then finally red to violet. And that's why it gets its name phenol red, because at most normal kind of neutralish pHs, it's going to appear in the orange to red kind of region. And so with this color change, we can get a generally good idea right around the pH of 0.1 units just by monitoring the color change as we transition. But it's a relatively limited window, 6.8 to 8.6. That is the range of colors where we actually see the change. If it looks yellow, it can be anywhere between pH 6.6 and 1. And if it looks violet, same thing. It can be anywhere from 8.6, 14. So lots of different indicators exist. We generally pick indicators based upon what we call their pKa, their midpoint. Where is it that we see that color transition taking place? And one of the reasons we use indicators is mainly for their ease of use. You got a chance to use pH probes yesterday. They're a little bit bulky and cumbersome. Imagine trying to do a titration around that swing arm of the pH meter. You can do it, especially if you have a big enough vessel, but it's going to be a little bit cumbersome. And it's also going to limit the kind of vessel you can do the titration in. Most of the time we did titrations in Erlenmeyer flasks. Can't do that with a pH probe because where's the burette going to go? So we use indicators for a lot of times that kind of thing. But the indicator's only good if the equivalence point for that titration is going to be at or near the active range of that indicator. And so let's take a look at some good examples and some not so good examples. Here we have a weak acid, strong base titration. In that weak acid to strong base titration, we have two options. We could use phenolphthalein, which is kind of our indicator of choice most of the time, or we could use methyl red. If we use phenolphthalein, we will see that the color change of phenolphthalein going from colorless to pink to dark pink, that transition happens right around the proposed pH of that equivalence point, which is why we're training you, look for the first sign of coloration. Why the first sign of coloration? Because, well, that's exactly where the equivalence point should be. By contrast, methyl red changes colors here between 4.2 and 6, which means that it'll have already changed color and we won't even be at the equivalence point yet. So that's not a good indicator choice for us. But if we flip it around and we do a weak base titration with a strong acid, we'll basically see the opposite phenomenon taking place. Phenolphthalein will change from pink to colorless well before we actually hit the titration endpoint or equivalence point. But methyl red will change colors at exactly the right time. Now, the other problem with phenolphthalein in this kind of application is the detection issue. It's a lot easier to see something become colored than it is to detect something becoming colorless. And so phenolphthalein would be a poor choice anyway, just because that's the color transition that we would be seeing. We'd be seeing it going from colored to colorless. How do I determine exactly when that is easily? All right, so I've got a question for you. This isn't a top hat question. We're just going to discuss it together. If I'm looking at methyl red, is methyl red a suitable indicator for this strong acid into strong base titration? Just give me a show of hands here. How many of you think methyl red would actually be a useful indicator in this circumstance? Okay, I've got 2 positive and 1 kind of okay, sure. The correct answer is yes. Now, why is it a good indicator here? Or why is it a suitable indicator? Well, we have to consider what the titration curve is showing here. We are talking about a transition that'll start to occur, maybe let's say right around here on the actual curve. From a milliliter standpoint, because again, we wouldn't be using a titration curve here, actually. We would be using just a normal titration, add in the indicator, see what happens. From a milliliter standpoint, how far apart is that blue dot from the actual equivalence point? Not really very far at all. We're talking about fractions of milliliters, most likely. So from that perspective, if we're doing just a normal titration, trying to find the concentration of this base using this acid, or vice versa for that matter, this would be an okay choice. And the reason it would be an okay choice is because while it isn't perfectly in the zone, quantitatively, we're talking about a very minimal difference in the actual amount of base or acid being added to get to this spot. And it's for that same reason that if we flip this around and we were doing a hydrochloric acid in sodium hydroxide kind of titration, like what you did in Chem 105, phenolphthalein would be just as suitable for the exact same reasons. And that's why we didn't give you a different indicator. Even though we could look at this indicator list and say, you know what, bromothymol blue seems to change colors right around pH 7. Why not use that? True, we could. We absolutely could. But phenolphthalein would work just as well in terms of giving us an accurate result. All right, let's take a break here. Let's say 10 minutes. Come back at 10:20, and we'll start up with the calculations in titration curves.